All right, let's talk about something that separates good coders from great ones. We're going beyond just writing code that works. We're going to explore the art of choosing the right tools to write code that's not just functional, but smart.
You've heard this old saying, right? It's about a cognitive bias called Maslow's hammer, and it is such an easy trap to fall into as a developer. You get comfortable with one tool, one approach, and suddenly you start using it for every single problem, whether it's actually the right fit or not. And that's really our whole focus today. Because truly great software, it isn't just about how well you can sling code. It's about strategic thinking. It's about looking at a problem and knowing exactly which tool, which data structure to pull out of your tool belt. To really wrap our heads around this, let's frame it with a scenario. And it's a big one. I want you to imagine you're in charge of logistics for the very first human colony on Mars. The stakes couldn't be higher.
So here's the deal. You've got one crate, and it has a rock-solid weight limit, 1,000 kilograms, not an ounce more. Your job is to pack it with food, and the only goal is to cram in as many calories as possible for those colonists. Oh, and here's the kicker. The food is pre-packaged. You have to take a whole box or you leave it behind. No half measures.
Okay, so these are your options. You can see the weights and the calories for each. Now, your first instinct might be to just, eyeball it, but let's see how those quick, intuitive ideas actually stack up.
And this is exactly where our intuition can lead us astray. A so-called greedy approach seems totally logical, right? If you just grab the item with the most calories, the potatoes, you use up most of your weight limit right away and end up with just over 1.7 million calories. Okay, what about a smarter greedy approach? Let's pick the most calorie-dense stuff first. That gets us a lot further, up to 2.8 million. Better, but still not the best. The truly optimal solution is to take the rice, the wheat flour, and the beans. That gets you to a full 1,000 kilos and over 3.2 million calories. And notice, neither of our simple, intuitive strategies found that solution.
So, you might be thinking, whatever. I'll just get a computer to check every single combination. That's the brute force method. But here's the problem. The number of combinations blows up fast. With just our 7 items, it's 128 combinations. Manageable. But if you had just 32 items to choose from, you'd have to check over 4 billion possibilities. That's not just slow, it's computationally impossible.
And this brings us to a really crucial point. Sometimes the best solution isn't a more powerful computer or a fancier algorithm. Sometimes the best solution comes from stepping back and actually changing the rules of the game.
Imagine an expert walks in, takes one look at your problem and just asks this one simple question. Suddenly the whole problem changes. What if you weren't stuck with those prepackaged boxes? By allowing ourselves to, say, take fractions of items or just scoop out the food, the problem becomes way simpler. Now the solution is easy. Just keep adding the most calorie-dense food until the crate is completely full. And look at that, we get an even better result, over 3.3 million calories. It's such a powerful lesson. Always question your constraints. Sometimes the most elegant solution is hiding in a requirement you thought was set in stone.
Okay, let's bring this all the way back from Mars and land it right on our keyboards. Because this kind of optimization problem, well, it shows up everywhere in software development, often in ways you might not expect. Let's look at a really common one.
Think about a bug tracking system. You've got a long list of tasks, and each one has a severity level. But this list is alive, right? New, critical bugs are popping up all the time. Old bugs get reprioritized. A simple list that you have to resort constantly, well, that's just not going to be very efficient.
What we need here is a data structure that's built for this kind of dynamic chaos. A structure that, no matter what you throw at it, always knows what's the most important thing to work on next.
But before we name the tool, here's a fantastic metaphor to keep in mind. Think of data structures as the nouns in your code. They are the things, the way your data is organized. Algorithms, then, are the verbs. They're the actions you perform on that data. They absolutely need each other to work. The abstract tool, the idea we need for our bug tracker, is called a priority queue. The concept is super simple. You can add new tasks whenever you want, but when you ask for the next item, it always gives you the one with the highest priority, no matter when it arrived.
So how would we actually build one of these? Well, let's look at the trade-offs. If we just use a simple, unsorted array, adding a new bug is super fast. But finding the most important one, we have to look at the entire list every single time. That gets slow. Okay, what if we keep the list sorted? Well, now finding the top bug is instant, but adding a new one means shifting everything around to keep it in order. Also slow. But look at that third option, a balanced tree.
It gives us this beautiful middle ground where both inserting a new item and finding the top one are incredibly efficient, even as the list gets huge. That's our winner.
And the ideal concrete implementation, the perfect noun for our priority verbs, is a specialized kind of tree structure called a heap.
Conceptually, a heap is a tree that follows one simple, powerful rule. Every parent node always has a higher priority than any of its children. That one rule guarantees that the most important item, the highest priority bug, is always sitting right at the top, at the root of the tree.
But here is the most brilliant part. While we think of it as a tree, under the hood, a heap is actually implemented as a simple, compact array. This is amazing. It gives you all the logical power of a tree structure, but with the raw speed and memory efficiency of an array. It is literally the best of both worlds.
And just when you think that's as clever as it gets, the thinking doesn't stop there. The most common type of heap is a binary heap, meaning each node has 2 children. But who says we have to stick to 2? What happens if we generalize that idea?
This leads us to something called the D-way heap, where nodes can have 3 or 4 or any number D of children. This lets you get into some really fine-grained performance tuning, optimizing for things like the specific cache sizes on your hardware. It's just a great reminder that even the most elegant solutions can often be pushed even further. So, we've taken quite a journey, right? From a Mars mission to a bug tracker, from abstract problems to concrete code. The last and most important step is to take this way of thinking and apply it to your own work.
So what's the big takeaway here? Look, the goal is not to go out and memorize a textbook of data structures. It's about developing a critical eye. It's about getting in the habit of questioning constraints, just like with the Mars mission. And it's about consciously choosing the right tool for the job instead of just reaching for that familiar old hammer every single time.
And that really leaves us with one final question for you. What high-stakes optimization problem, what Mars mission is hiding in the code that you're working on right now? Find it, choose the right tool to solve it, and that's when you start writing truly exceptional software.